Hi, this is Prithviraj. Welcome to the session, and today's topic is Bellman-Ford algorithm under Module 4 Dynamic Programming. Bellman-Ford algorithm is used to find the shortest path from a single vertex to all other vertices in a weighted graph. This algorithm was mainly proposed by Alfonso Schimbel, but later published by Richard Bellman and Lester Ford. Hence, the name is given as Bellman-Ford. As we have studied about Dijistra's algorithm, Dijkstra algorithm is used to find the shortest path. But in Dijkstra, it doesn't work for the negative weight. The interesting thing about Bellman-Ford algorithm is it works for negative weights or negative edge in a graph. The distance can be calculated using the formula. If distance of u greater than distance of I plus cost of I comma u, then we can update the distance of u as distance of I plus cost of I comma u. Here is a problem. To find the shortest path from node 1 to every other nodes in a graph using this Bellman-Ford algorithm. And here in this graph we can observe some of the cost having negative values. So we have negative weights on some of the edges. Let us take the graph and let us take one array called D array, so that each time whenever we find the shortest cost minimum cost that we are going to update in this array. We'll take the array D array with the starting vertex as 1. Initially the distance from 1 to all other vertices will be infinity. From 1 to 1 the distance will be 0 and all other remaining values will be infinity. Consider the vertex 1 as a parent vertex and find the distance to all other vertices. That means let us take I is equal to 1. And we have to use this form to calculate the distance, new distance. First, if distance of 2, that means initially we have taken the vertex as 1. From 1 we have to calculate the shortest path from to all other remaining vertices. If distance of 2, if it is greater than distance of 1 plus cost of 1 comma 2, we are just substituting the value for I and u. Here I indicate 1 and u means the next vertex, that is 2. So infinity, which is greater than 0 plus 2, and the condition is true, so distance of 2 is updated to new distance, that is the minimum distance, that is 2. So instead of infinity we have updated the distance as 2. Next, now from 1 to 3, again apply the same form. If distance of 3 greater than distance of 1 plus cost of 1 comma 3, cost of 1 comma 3, that is from 1 to 3, the cost is 4. So distance of 3 initially it was infinity, so infinity greater than distance of 1. Distance of 1 we can observe it in D array, that is 0, plus cost of 1 to 3. So cost of 1 to 3 is 4, so 0 plus 4, the condition is true, so distance of 3 is updated to new distance, that is 4. Next, now from 1 to 4, distance of 4 greater than distance of 1 plus cost of 1 comma 4. Distance of 4 initially it is infinity, that we can observe it in D array, and distance of 1, that is 0, cost of 1 to 4. So cost of 1 to 4, that is infinity. We don't have a direct path from 1 to 4. So the condition is false, infinity greater than infinity, it is false. So distance of 4 remains as it is, that is infinity. Similarly for distance of 5, from 1 to 5 we don't have a direct path, hence it remains as it is, distance of 5 equal to infinity, and similarly for distance of 6. Okay, so this also becomes that will be remains infinity only. And one thing you can observe in this array, after the one iteration, we can observe one thing: vertex 2 that gives a minimum distance compared to all other vertices. Vertex 2 that gives the minimum distance, and we have already computed for vertex 1. Now the step 2: consider vertex 2 as a parent vertex and find the distance to all other remaining vertices. Let us take I value is equal to 2, and we have to apply the same form once again and perform the same iteration. From now we are calculating from 2 to 3, 2 to 4, 2 to 5, and 2 to 6. Now initially, let us take the distance, let us take u value as 3, because we are calculating from 2 to 3. Distance of 3 greater than distance of 2 plus cost of 2 to 3. Distance of 3, which is 4 in a given D array, which is greater than distance of 2. Distance of 2 is 2 plus cost of 2 to 3. So from 2 to 3 the cost is minus 3. So there is a negative cost, minus 3. So 4 greater than minus 1. Hence we will update the distance 3 as minus 1. So instead of 4, we have updated it as a minus 1. Next, from 2 to 4. Distance of 4 greater than distance of 2 plus cost of 2 to 4. Distance of 4 is infinity, greater than 2 plus 1. Distance of 2 is 2. Cost of 2 to 4, as we can observe in the diagram, cost of 2 to 4 is 1. So infinity greater than 3, that is true. So distance of 4 will be updated to new value, that is 3. Now let us take the cost from 2 to 5. So distance of 5 greater than distance of 2 plus cost of 2 comma 5. Distance of 5 is infinity in the array, which is greater than distance of 2 is 2 plus cost of 2 to 5 that we can observe in the diagram, that is 5. So infinity greater than 7, distance of 5 is equal to 7. So update the new distance in a D array as 7. Next, from cost 2 to 6. So distance of 6 greater than distance of 2 plus cost of 2 comma 6. Here we'll get infinity greater than infinity, so the distance of 6 remains as it is, that is infinity. And at the end of this iteration we have to find out the minimum value. So apart from the vertex 1 and 2, the minimum value which will given for the vertex 3, that is minus 1. Step 3: consider the vertex 3 as a parent vertex and find the distance to all other remaining vertices. Let us take the I value as 3. So from 3 to 4, we'll calculate the distance. Distance of 4 greater than distance of 3 plus cost of 3 comma 4. Distance of 4 is 3, greater than distance of 4 is distance of 3 is minus 1 plus cost of 3 to 4. Cost of 3 to 4 is minus 4. So we'll get 3 greater than minus 5. So distance of 4 will be updated to minus 5. Next, from 3 to 5, distance of 5 greater than distance of 3 plus cost of 3 comma 5. Distance of 5 is 7, greater than distance of 3 is minus 1 plus cost of 3 to 5. 3 to 5 is minus 2. 7 greater than minus 3, so the condition is true. Hence we have to update the distance 5 as minus 3. Next, from 3 to 6, distance of 6 greater than distance of 3 plus cost of 3 comma 6. So distance of 6 is infinity, which is greater than minus 1 plus infinity. So the condition is false here. Distance of 6 remains as it is, that is infinity. And at the end of this iteration, in this D array we can see vertex 4 will give the minimum distance. Step 4: consider the vertex 4 as a parent vertex and find the distance to all other remaining vertices. At the end of each iteration, we have to consider the minimum distance, and whichever the vertex having minimum distance, and in the next step we have to consider that vertex as the parent vertex. And here we'll consider, I will take I value is equal to 4 and calculate the distance from 4 to 5. If distance of 5 greater than distance of 4 plus cost of 4 comma 5, distance of 5 is minus 3 greater than minus 5 plus infinity, so the condition is false and the distance 5 remains as it is, that is minus 3. Now from 4 to 6, distance of 6 greater than distance of 4 plus cost of 4 comma 6, that is distance of 6 is infinity and distance of 4 is minus 5 plus cost of 4 to 6. Cost of 4 to 6 is 8. So infinity greater than 3, that is true. So distance of 6 will be updated to new distance as 3. And in this D array, the vertex 5 that gives the minimum distance, because we have computed for vertex 1, 2, 3 and 4. Next we have to consider only for 5 and 6, and out of this 5 gives the minimum distance. Step 5. Consider vertex 5 as a parent vertex and find the distance to all other remaining vertices. Let us take I value is equal to 5. Now from 5 to 6, if distance of 6 greater than distance of 5 plus cost of 5 comma 6, distance of 6 is 3 in the D array, greater than distance of 5. Distance of 5 is minus 3 plus cost of 5 to 6. From 5 to 6, the cost is 6. So 3 greater than 3, which is false. So distance of 6 remains as it is, that is 3. So that's all, because we have computed for all the vertices, and finally only one vertex is remaining, and in that vertex uh, uh, it's not necessary to calculate the path or the distance, because that itself gives the final the array. Final graph can be rewritten with the minimum cost, so that we can get the shortest path from one vertex 1 to all other remaining vertices. So here we can see that is vertex 6 is the last vertex, so there is no other vertices remaining, so it is not necessary to calculate the shortest distance. And this is the final array, final D array, and based on that we have rewritten our graph along with the shortest cost. So from 1 to 2, that is 2, from 1 to 3 minus 1, from 1 to 4 minus 5, 1 to 5 minus 3, and from 1 to 6, that is 3. Thank you.